here is Valerio Lucarini, which I guess everybody knows. And so it's going to talk about response theory and
Yes.
what you see in the title.
What you see in the title, exactly. So good afternoon. So today I will try to give a summary of some result, old, less old, and quite new on predicting the response of systems to perturbations. So the starting point, the theoretical starting point is the classical fluctuation dissipation theorem. But as you will see, there's been a lot of development. So it has been possible to greatly generalize this kind of work and to address different limitations of the classical theory that I'll try to spell out during the presentation. So first of all, what is the response theory? So this is something I learned in this form from David Ruel when I attended a long seminar at the Poincaré Institute in 2007. So I suggested to think, John, in this way. So response theory is like a thought experiment. So you have a system you control, you have a knob you can tune to control a parameter, you apply a protocol to this parametric modulation, and you have a measuring device to observe the system. This measuring device can measure just one quantity of many quantities, or ideally the entire field. Okay? And then the goal, what is response theory, is a sort of a magic tool that allows you to predict the measurements you're going to make from the other ingredients you have put into the system, from the knowledge of the system and the way you have technically prepared it, from the perturbation you apply, and from the temporal protocol of this perturbation. So the one fundamental issue is that this sort of magic tool, this black box, does not allow by itself to distinguish the roles of different modes of variability of the system. So we want to disintegrate this operator into many terms. And there is a long history, of course, here. And the starting point is the work by Kubo in the 50s, studying the perturbations of the canonical ensemble. He derived what is, let's say, the modern form of the fluctuation dissipation theorem. By studying the natural fluctuations of a system, you're able to predict its perturbations. In particular, the response operators are correlations, are a special form of correlations. Much later, the theory was extended to chaotic dynamical system. This proved very, very challenging by David Ruel in the 90s. And then a new viewpoint on this was developed, taking the angle of the transfer operator. So basically lifting the problem to a functional analytical approach. And this has allowed a major extension of the theory. And then there's been many variants here. What if the dynamic, if we relax some properties, is it still possible to derive this kind of relation? So a matter of fact, the idea is that these kind of properties are almost pervasive on many systems. So it's actually, the range of application of the theory seems to be way more extended than what the theory says. An important aspect is that if we treat, let's say, suitable stochastic system, everything becomes miraculously easier. Okay? Now, what are the kind of questions you can address? There is a large variety of questions. One is, actually, that's how I started my work. So you have an optical material, you apply an electromagnetic field. The electromagnetic field is typically an incoming wave. You measure the index of refraction. That's what an experimentalist does. And you can predict the index of refraction by using response theory on the condensate matter. Okay? Or you can predict the atomic absorption lines, as an example. So slightly, let's say, less classical. I have a bridge. I apply mechanical forcing. The forcing is the forms of many repeated shocks of people walking over the bridge. I measure the mechanical strains, and indeed, I can predict what is the sensitivity of the system using response theory applied to the mechanical structure, and you learn that you should never march on a bridge. And that's actually one of the starting point of tipping points, by the way. This is the Millennium Bridge. and they had to perturb it because it was too perfect. So it was getting fantastic resonances. But indeed, and this is work I've done with Francesco originally, it's possible to use this kind of formalism to predict climate change in an ensemble sense. So you can apply this for out of equilibrium system with many degrees of freedom. But let's go to the challenges. So I have used the color code. So one problem is the interpretability. One problem is the fact that all of this theory is very equations heavy. There is almost a fetish of equation. I'm a fetishist myself of equations, but it's sort of written in a very convoluted way that might seem almost like a circular argument. Are we able to translate the problem into a different formulation that is amenable to data-driven approaches, okay? Where I don't know the equations. The equations don't even exist, and I shiver to this idea. So other point that was also mentioned in the previous presentation, most of the derivations are done you assuming a Gaussian noise when I consider a stochastic system. Is this the case? Can we extend the theory to treating more general noise, and in particular alpha stable noise that are of great interest in Leicester, especially because of the work by Larissa. Now, and the last point, which is in some sense the more radical one, is the reference state. So all the literature, with the important exclusion of this paper by Michel Branick and Uda in 2021, assume that the reference state is at steady state. So I have a steady state, and then I perturb it. Can we construct a response theory with predictive power for systems that are not at steady state? So the reference state can be periodic or aperiodic, and on top of it, I apply further perturbations. Can I still formulate still have equations that have predictive power in this context? So we'll try to tackle these challenges. And the last, let's say, the main progress in the last year and a half has been in the last three challenges, whereas the interpretability is something we learned to face earlier, especially thanks to the work of Manuel, who is in the room in his PhD thesis, with the major contribution. That's Manuel. And then the work was extended by other people in the room that will be mentioned. But Manuel is the main person here. So now, let's try to provide a simple recipe for a linear response theory in a sort of a classical framework. I start with a diffusion process. I can make different assumptions. Let's assume it's an elliptic diffusion process, even if one could be a bit more general. So the evolution of ensembles is driven by the Fokker-Planck equation that corresponds to the Langevin equation. I assume there is a unique invariant measure that obeys the equation you see on the right, and then I add a perturbation. As an example, I perturbed the drift with a small perturbation, which is in general time dependent. Well, it's possible using a sort of standard methodology, the so-called using the Dyson expansion. It's possible to find an explicit expression for the perturbation of the measure. So now the new measure is not anymore invariant because it depends on time, but the correction is proportional to the intensity of the perturbation and averages to 0 by construction. Okay, and a side story that indeed Manu developed is that if instead you perturb the noise law, so you're a bit, it physically corresponds to perturbing the fast degrees of freedom in the Hasselmann sense, you can still find a corresponding formula, which is actually quite interesting and much less studied. So this is in the ideal world where I know how measures change. So if I have full information on my system, but as I said, in the real world, in any experimentally reasonable context, I observe the system by looking at some quantities, which we call observables. And then, as an example, you are able to find formulas which are this generalized form of the fluctuation dissipation theorem that tell you that the perturbation of my observable is given by a convolution product of a green function and the modulation. So this is the fluctuation dissipation theorem literally in one page. Now, the issue is I would like to translate this knowledge on the change of expectation value of the observables into something that is disintegrated in different modes. So I would like to say, how do different modes of variability of the system, and in climate this is sort of a common question, contribute to the change in the expectation value? So the key here has been to learn from the colleagues actually who are in the other rooms here, from Mesic, from Colebrook, and from a few others who basically taught us how to talk the language of basically the Kubman-Kolmogorov operator. So the idea is to write the observable as a suitable combination of eigenfunctions of the Kubman mode. So this is the key thing. So the Kubman modes give me let's say, a base to represent observables. I decompose my observable in these modes, and then magically it becomes a problem that can be written in terms of eigenvalues and eigenvectors. So think, without going into the details, of course, the literature on how to perform the Kubman analysis is immense. And as I said, we are the luckiest person. Next door, we are the leading experts. But the fundamental result we get here is the following, is that when I apply my evolution operator to my observable, this thing breaks down into a sum of exponential terms where the time constant depends on the eigenvalue of the Kubman modes. So now I go from a green function, which is a sort of a mysterious form, into an object that is going to look like sum of exponentials. Now, the sum of exponential is very attractive because the characteristic time scales do not depend on the observable, do not depend on the forcing, depend only on the system itself. This universality in the representation is also a highway to understand the occurrence of tipping points, which are not discussed too much today, but the tipping point occurs, the B-tipping in particular, when one of these objects goes to zero. And this is the critical slowing down in a functional analytical form. And this is a very potent way to understand this. Now, as I said, this is how we're going to get the green functions. Now, there are some side stories here. If a green function is a sum of exponential, and assume I have my green function, and I have a methodology to write it, to extract these time scales, and there are ways, the so-called Prony method, as an example, I'm able to derive from a green function the characteristic time scales of my system. So I'm literally doing a decomposition throughout the modes. Okay, so this is this adds on the I interpretability and D the data-driven approach, because the Kubman, the magic of the Kubman is that it has why it has become so important, because it's on one side theoretically powerful, on the other side there is the black magic of constructing these modes. So now we can take this black magic and use it to study the response. Rather than studying the doing prediction on the system, we use it to study how the system will respond to perturbations. So this is the key element here. Okay, sorry. Yes. So, and this is indeed the sort of final result we got here. So writing this green function as a sum of exponentials, being able to reconstruct this coefficient and this lambda from the Kubman analysis of the system. So what is the predictive power here is that if I'm giving the system and the form of the perturbations, I'm able to build the green function without doing the experiment. So this has been, we performed this in these two papers that came out almost at the same time. And we were sort of very surprised this would work. It takes time and effort because doing this calculation is very non-trivial. But this is something that is very encouraging. On the other side, if you take this green function and you apply, you see that it's sum of exponential, you apply a Fourier transform, you get that the susceptibility, so the Fourier transform of the green function is a sum of resolvent. So you have again another universal form. So even if I'm taking a very general system out of equilibrium with general perturbation and so on and so forth, the response is a sum of effective harmonic oscillators. So this is one of the most boring results you can obtain, but instead it just tells you, it tells you that the response is the weighted sum of the contributions from all the internal modes. It's actually exactly identical to the form, to the sort of perturbation theory you have when you study atomic spectra. But even if this is non-Hamiltonian and it's a total mess, still the result is the same. Now, switching from response to correlation. As I said, the green function is a strange correlation. So everything I said applies also if I look at the correlations of quantities. So this is originally mostly the work of Michael Chekroun and previously of Alexis Tanté. And the idea that they proposed and that we also built on was that you can write the general correlations of two quantities, f and g, as a sum of exponentials. So again, what you see, these are the same exponential factor you see in the response. You're just looking at the correlation, so you don't need to do a response experiment. And again, it tells you that the occurrence of tipping point, the critical slowing down, so this is the angle of the Ruel-Polycott resonances, happen when you have that the spectral gap goes to zero. And typically it will happen in two ways. Either it's an exponent with the zero imaginary part, or it's a pair of exponents with the opposite imaginary part. In one case, you will have an oscillatory instability. In the first case, you're going to have just the regular instabilities. Okay, so this is sort of the link between response theory and occurrence of tipping point. And I see these as two complementary ways. Either you see the tipping point as something, a place in parametric space where a little push leads to basically an instability, or equivalently as a place where the correlations don't decay anymore. Because any forcing will sum up the effect exactly because the correlations don't decay. So this is a first step. And I think the key thing here is that the interpretability through this Koopman expansion, you are able to tell which is the critical mode. So there is one or a pair of specific critical modes that are in the climate change literature called exactly the critical mode of variability that is associated with the tipping point. Okay, please.
So in this theory, I understand when your state becomes unstable, this happens with correlations. But what happens if your state disappears altogether?
This is, okay, that's important. You are before. So this is a local theory here. So it's a theory that where your state loses stability. You don't know anything about what's happening afterwards. To go into that, you need a global angle. So you need to introduce notions like edge states, and we discussed in other contexts, and Reich is the person to talk to on this matter. So now, okay, so far we have the interpretability, but I want to focus on the data-driven method. So I came to study, thanks to some interaction with Alessandro Laio from SISSA Trieste, this notion of Markov state modeling. So this Markov state modeling is something that's very much used, especially in chemical physics. And the idea is that you, rather than studying the dynamics of a system, you partition the phase space using typically some Voronoi tessellation, you study the transitions between these Voronoi cells, and you derive an effective Markov chain model. So once you have the Markov chain model, basically, and you verify it's a good Markov model, you know basically everything on the coarse grain properties of the system. Now, the cool thing here is that in fact, all this Markov state modeling is another Koopman analysis. So usually the dictionary that is used to do the Koopman analysis are polynomials, say, or monomials of different, or there are implicit methods like kernelized method. But if you choose instead as dictionary of your Koopman analysis the characteristic set, characteristic function over some sets, you derive automatically Markov state modeling. So Markov state modeling is a special case of Koopman analysis. So now, why is this cool? First, it's a nice way to explain it. But the other thing is that if you develop a perturbation theory for Markov chains, so forget about this analysis. So now you develop a perturbation theory for Markov chain, you have a tool that you can automatically transfer and use to study in principle any arbitrary system if you're happy with Markov state modeling. So this is the idea. So I'm moving the problem from the continuum to the discrete in space and time. And if I'm happy with that level of discretization, I can unleash the power of Markov chains. And Markov chains have several advantages. First, it's one of the most studied, I think, system. Second, it's matrices. So we have software to treat matrices basically of arbitrary size and with very high precision. And perturbation theory for these matrices is easy to derive, okay? It's just, it's doable. You need basically to solve some recursive problem and find a closure. These are long formula. I'm not gonna put it, I'm just telling you how to do it. So anyway, the message is using Markov, by looking at the problem of Markov state modeling as a special case of Koopman, we have both the advantages of Koopman and of Markov chains. Koopman for interpretability, Markov chains for easy, let's say, how easy it is to do formal calculations. So then we tried, after all this chatting, we tried to do the exercise. So we took, at this stage, a simple model, a relatively simple. It's a model actually that is always surprising. Anyway, a classic Lorentz 63s plus additive noise. Additive noise, we wanted additive noise to have a smooth measure. Then we applied all the arsenal I described. So we did the Koopman analysis with different dictionaries, with different, let's say, level of precision, as well as with Markov chains. So the goal was to find the spectra, to find the Koopman modes, to find the Koopman eigenvalues, and then use them to construct the response operator. So it's many steps here, and it has taken a couple of years. So summarizing this into slides, the result is basically what you see in these confused pictures is that basically, as you increase the maximum order of the Koopman expansion, you get a good convergence of the leading eigenvalues. And these leading eigenvalues agree quite well with the eigenvalues you get from the Markov state modeling analysis. So somehow you have a nice, coherent picture of this system. What is the message is that depending on the system you're looking at, it might be better to use one methodology or the other, but there is robustness. And the robustness is proved by, so these are the modes that you compute. But more interestingly, you get extremely accurate and extremely, let's say, robust green functions. So this is the first example of green functions computed using this methodology. So building each block from each of the Koopman modes and using the equation. So, and then testing it against the experimental response function. So this was, we were very happy and very surprised. And we saw that as expected, as you increase the resolution, you tend to get, let's say, you tend to cover more time scales. Okay. Okay, this was one thing. And something that is still unpublished. So I'm going to look at John. Where is John? Yeah, John. Let's look at John. He's going to blush now. But this is still unpublished and it's on his desk. But it's a very important result he has obtained. So, and I'm very happy, is that he has been able to construct this response operator also for a much higher dimensional system like the Lorentz 96. And is also trying to do the same for Kuramoto. So the idea is, if we are able to break this through, you know, the tens or maybe 100 degrees of freedom, it seems to provide good support to the fact that it is possible to construct a response operator also for highly dimensional system. Okay, so this is, let's say, the part where we tried to sort of break the barrier of dimensionality and improve the interpretability of this response operator and being able to point with our finger to which modes are most relevant. So this is also a way to do model reduction, basically. Yes, please. It's actually what happens is most of the computational cost lies in doing the Koopman analysis. But then it's integrals to be computed. Now, the good thing is then, like our claim is, if you're happy to do Koopman analysis, then you would get almost for free all the response. So the idea is, instead of being only, so to say, able to predict the evolution of your system, you are able to predict the properties of the cloud of points near it. That's a bit the idea. Okay? Okay. So now, and here a great friend and a great scientist comes again into the picture, Michael Shekroon. So Michael is proposed a challenge to myself some time ago, and it took time to solve it. But the message is, why are we obsessed with, we're always obsessed with Gaussian process. Gaussian process have a lot of good and bad properties, but it's a sort of always the lazy solution to modeling a system with, of course, it's the standard sort of Hasselmann ansatz, but we know that many systems have different kind of noise. So the problem was, is it assumed now that my stochastic system has some Gaussian noise and some Levy noise. So sometimes it receives some horrendous kicks. So if you look at the evolution of this system, it's incredibly irregular. So it doesn't look like, you know, sometimes it jumps everywhere. Still, question is it possible for this class of system to write response theory for perturbations to the drift, and this looks sort of reasonable, and perturbation to the noise law, to the Levy noise law. So this seemed a more challenging, daunting task. So the story is, after 20 pages of calculations, the answer is yes. So it's possible to write green functions in both cases. So the answer is, even for these very regular processes, there is a regularity in the response of the system to perturbations. So we tried to test it in one of our favorite models, so the Gill-Sellers energy balance model, which is one of the key original model, if you want, of climate science, describing the energy balance in the north-south direction. By the way, this model has been key to understanding multi-stability of the Earth system. But here we focus only in the warm branch. And so we take this system, we add noise, and we try to construct green functions. And the answer is that if you consider a system with purely Gaussian noise, unsurprisingly, you can construct the green functions to, as an example, perturbation in the CO2 or perturbation to aerosols. And it's possible also to do the same, even if the green function will definitely look different because the reference measure is different and the statistics is different, also in the Levy case. So somehow there is a convincing argument, theoretical argument, and an argument that so it's verified by numerical, not entirely trivial numerical integrations, that it's possible to develop a response theory for this case. And indeed, it is possible also to construct the Kolmogorov modes, to find the decay, to find everything. So even for this system, the combo Koopman analysis and response theory stands. Okay? And this is, I think, very encouraging for the interpretability, for the fact that we are able to treat a different kind of noise, and also because it is amenable to numerical treatment, data-driven analysis. And now let me go to the last topic, which is actually something that has happened only that I started to work on at the beginning of 2026 after visiting Great Bay University. Jin Chao is there, and I had a chat with Misha Branicki, who was in Edinburgh, who is in Edinburgh still, and we were discussing about response theory. Misha had a collaboration with Andy Maida, so he knew very well in and out the topic. And so he said, yeah, you're proposing these results, but you're always making the assumption that response that you have as a reference state a stationary state. I said, yes. And he said, yeah, but this is actually not a very good hypothesis. I said, well, yes, because if you have a system with seasonal cycle, which is pretty common, the reference state is not a stationary state because it has a periodicity. And then when he was telling me this and, bit bashing, I thought, okay, it's even worse than that, because when I talk about the climate system, I always like to say it's a multi-scale system. So if I focus on one component of the climate, there's always going to be some modulation, fast and slow, that is outside my system of interest. So actually, my whole argument is screwed. I talk about how multi-scale and rich the system is. I develop a response theory for a stationary system, and then I want to apply it to that. So I was like, oh my God, that's not very good. Well, I mean, of course, it's nothing. Nobody expects to develop a closed theory, but this is a major disagreement. And so I decided to give a try, and Michel had developed a theory, very important result that I think has not been sort of celebrated enough, a complete rigorous response theory for system with the periodic forcing under certain hypotheses. So the system has a periodic reference state, can be a very complex system, and then you add the perturbation, and you develop some formulas and conditions allowing for this to work. So then I said, okay, let's try to generalize this to a periodic forcing. So I decided to play with the toy I learned to like a lot, which are Markov chains. So there is a theory of time-dependent Markov chains, which is written like that, where the evolution operator depends on time. So you have at each instant a different transfer operator, okay? So at each instant, the probabilities evolve with a different law. And all the properties of my original system is written in the matrix Mn, which can be periodic, aperiodic, and of course, the stationary case is a special case. So can we now, so I have a system that, does something like this in time. I had a perturbation. I want to make sure that this perturbation does not explode. So the way to make sure that the perturbation does not explode should mirror the property that I have in the stationary case of non-zero spectral gap. So in the stationary case, the condition to have a response theory that converges, that the spectral gap is non-zero, so meaning that the system loses information, dumps everything. So in non-stationary case, it's not exactly like this. You need a different condition, which is basically associated to the fact that if I take two measures, I apply to them the same operator, the distance between the measures in total variation decreases. Okay? Yes. Yeah.
Very, very harsh.
Yes.
So
yeah.
most examples, I'm trying to look between those examples, of course, this would not happen unless you really punch it from this is
Well,
this is a sufficient condition, but completely not a necessary condition.
no, yes, no, it is sufficient.
It's difficult to understand whether this measure exists otherwise. So
Well, sorry?
it's difficult to understand precisely when these two-like measures.
Yes, yes, yeah. So of course. So the idea, the key thing is I need to have an equivariant family of measures that's supported on a pullback attractor. So in other terms, if I need that, wherever I start in the infinite past, after a certain time, my system converges to what I would call the covariantly changing measure. And then I study this perturbation, the perturbation over this measure. So this is the key condition here. Once I am happy with this, it is possible, indeed, doing some algebra to write the perturbation of the measure, the perturbation to the observables, and everything. So this is done for Markov chains, and then you can basically mirror it for time-dependent diffusion processes. This is the calculation here. It's a bit more annoying, and you get these horrendous time-ordered exponentials. Those of you who did quantum field theory maybe still have nightmares about that. So after 20 years, I had to write a TXP again. When I gave my exam in quantum field theory in Pisa, I shamelessly pretended I understood what it meant, but now it came useful 20 years later. But anyway, the idea is that you have to time order the action of the evolution operator to essentially to ensure the consistency of the equivariant measure, okay? No matter how ugly the formula looks, the message is, yes, you have a formula for changing the measure and for changing the observables. And it is, I mean, a reasonably good formula, except that, and this is essential, before you had that the response as was a convolution of the modulation of the forcing with the green function that depended only on t minus s, the time distance. This is lost. Since the system is explicitly time dependent, too bad, the green function depends on the time distance and on the time. That's the price you have to pay. It's a big price, actually. You can draw interesting conclusion in a spectral domain that we have not yet done. Anyway, the result is there. And then, again, once you have the formulas, as I learned, you have to try to apply them. And this can be very challenging and daunting. So again, I took my favorite model because I like it, because it's rich, because it has a long history. And I decided, okay, I take this model and I want to introduce explicit time dependence. So what I added to my model, you see on top the line is some oscillation in the solar constant, the solar cycles. And then you see these sort of negative spikes, and these are volcanoes. Okay, so every thought year, without any regularity, I have some volcanic events that reduce my solar constant, and after 2-3 years are relaxed. So this is a sort of actually both quantitatively and qualitatively, it's quite close to the history of the planet in the last 1,000 years. Okay, so now you have so now my climate is the blue line, is not a straight line, because the climate of the last 1,000 years is not a line. It has a lot of variability due to the natural forcings. So now the question is, my baseline is a system with natural forcing. I want to apply response theory on that. Okay, so what you see here is how the system evolves in time when you get these spikes. And I did a Voronoi tessellation of all my space in only 2 dimensions. So I did a very, very sort of coarse-grained version of the system. And then I applied my response theory by using the formulas I have derived. And the result is I applied first this kind of forcing, which corresponds to, you see the black line, an increase in the greenhouse parameter that then stabilizes and then goes back to 0 in a few hundred years. So this is a sort of an IPCC-like scenario. CO2 increases, stabilizes, and comes back. And I applied the formula, and I got, even if I'm in a strongly reduced space, a very good agreement between the prediction and what the ensemble, what the model says. So there was, I'll say, very good correspondence. So the perturbation applies until here, and I see I'm able to follow to a good degree of approximation, considering all the approximation I've taken, what's happening. So yes. Now, what if the time dependence is strong? Because one could argue, okay, you are putting these small perturbations, very small perturbations. So 1 degree, half a degree. So this is like a perturbative. So, you know, if you think in perturbative terms, you have developed a theory for a time-dependent system, but maybe at the end of the day, the impact of the natural variability is small because, you know, you're summing 2 perturbation theory. It's a fair point. It's a fair point. So then, with Stefano Galatolo, I was able to, I think, to learn much more. So with Stefano, I will mention the key results we obtained, but this is the numerical experiment we made. So this is now a simple 2D gradient system with Gaussian noise, but this is how the potential changes in a period of 70 time units. So it goes from bimodal to unimodal to bimodal on the other side. So this is a system that, if you want, goes through a lot of bifurcations in some sense. So the invariant measures change it dramatically. So it's a very strong perturbation. And what you get is that this is how the reference measure changes in time. And this is the response of the system in the measure to a perturbation. And this is the prediction of the response theory, and it's basically indistinguishable from what you obtain. So the idea is the theory works also in this case of extremely strong perturbation, extremely strong time modulation. So the hope is that it allows us to treat very strongly non-autonomous systems. Now, the 2 key results we obtain with Stefano is that yes, these, under suitable conditions, discrete time sequential system with memory loss do obey response theory. So this is a paper that is in Review and Communication of Mathematical Physics and seems to establish a strong, rigorous result. So this seems to be a sort of an extension, real extension of response theory for discrete time. And a very interesting result that if I take a continuum stochastic system and I apply Euler-Maruyama discretization, so this is the standard way to do simulations, it works. So the discretized system obeys the theory. The second result is that all unlike finite dimensional projections converge in the measure and in the linear response operators to the true system. So I'm very happy of these results because it tells that what we can do practically is always some finite dimensional representation of the system, because we like to believe in equations, but equations are an illusion. We're never going to get the equations in our practice. And somehow there is a result of convergence, which I find extremely encouraging. And this is done with Stefano, is Ian Easley, and it's in Journal of Computational Physics. Now, I think we are coming to the end. I'm just going to say the last word. The last thing is that there is something else. So one of the motivations behind the work has been trying to understand fingerprinting for climate change. So how do we relate signal and forcing? And the whole problem of detection and attribution of climate change is hey, who done it? You know, this is an old something from Sherlock Holmes. So who has done it? How can we do this result? So the key result, key idea of Hasselmann was to create a statistical methodology to do this analysis, which has changed climate science fundamentally. Is the pillar of the IPCC reports. So now the message is that it is possible to derive these equations and the detection and attribution equation from statistical mechanics, not only in the stationary case, but also in the case of a time-dependent system. So we have tools and algorithms, and I leave the last figure here because it's just a figure. This is the last figure. There is a way to assess for a time-dependent system that is explicitly time-dependent and undergoes extra forcings to attribute the impact of the forcing on a sliding time window. So to tell who has done what at which time, even if the reference system changes. So this is potentially a strong result that might be useful. And this is especially interesting also for systems like ecosystems where the time modulation is very strong. Okay, so this is the hope. I conclude by saying that the hope is now to use this theory to understand, and I have great expert in the audience, better or understands from a different angle, p-tipping and rate-induced tipping. That's my hope. I'm not done it yet. We're not done it yet. But the hope is to push the theory to the divergence and use this to understand the p-tipping and rate tipping. Thank you very much.
So we have about 10 minutes, I will say, for questions. So starting.
Yes, I have a question and first a remark and then a question. So I think what you said about the time-dependent Markov chains, I think you can arrive at a complete theory if you have, if the time dependence is basically through a stationary or ergodic stochastic process, right? So if you have a driving process underlying, let's say, that drives your Markov.
Yes.
Your Markov, the M, right, depends on N through basically an ergodic stochastic process. And then
that is one way that allows you to get to the endpoint. I agree.
And this
because if it's a perpetual drift, it's not going to work.
It's not going to work.
Yeah.
But this stationary or stationary ergodic case does include the periodic case. And I think the condition you had about the Dovruchin coefficient, you can generalize. It is enough if that coefficient is smaller than 1 on average. If the geometric average is smaller than 1.
Okay, this is let's say this is probably true. I'm not. One has to be a bit careful with the computation. Now, of course, if it's periodic, you think it's. The issue is, I would like to use the difference between this condition and the stricter condition I have imposed exactly to understand the p-tipping. So the p-tipping tells me there is a period, a moment, a phase in the period where my system is less resilient. So my hope is to compare these two and find this, this critical phase in the period. But I'm not there yet. Yes. Thank you.
Any more questions?
Yeah, just a comment. Yeah, so it's similar to what was asking about. There's some conditions that you imply here, which basically says that the statistic or this transfer operator converges to some kind of moving fixed point, right? So you have a random fixed point for this transfer operator.
Yeah.
And this, of course, is nice if it happens. It may not happen at all.
Yes.
And so if you have some instability in the system, then actually what happens is that also the conversion will be not uniform. So you will have no clue when things converge. So it's very difficult to make any statement to make finite time of where these things are. So the sum of these limits also take time to infinity, say almost sure convergence. That's very cool, but it doesn't mean that if you run something, so one has to be a bit careful. It's interesting to see to what extent these things actually work, even though they may not theoretically always work, or even the theorems don't apply. So.
No, so to address this, the way to prove things is to go from perturbation theory on the transfer operator to perturbation theory on a sequence of transfer operators. So it's a lifted transfer operator that acts on sequences. Then you perturb that. Yeah. I mean, no. I agree. So the idea is, if you assume that the equivariant measure exists and is sufficiently stable, then you can do this.
Even if it not exists, there's still interesting things to say.
No.
What would happen is you had some statistical mixture of measures that you converge to, like an interesting attractor of indispensable measures, and this could still have two aggregate properties, but then you cannot look for this one measure.
Yes, okay,
It
yeah.
is something that the average, some kind of funny average of these things exists. So
Yeah.
this is
That's
all in.
been,
When I'm to system theory, people looked at this for a long time.
Okay. No, I mean, that's, beyond what I've been able to do. But yeah, thanks for this. Toby.
I have a question to the fingerprinting. So is the idea in some sense that you see a signal and then using the response operator, the inverse of the response operator, and sometimes you see which perturbation should have happened.
So the idea is the idea of the optimal fingerprinting is that you assume that the signal is a linear combination of some fingerprints. The fingerprints are the ensemble averages of the response of your system, of say your model, to one specific perturbation. So there is an assumption of linearity there. Okay. So now in the earlier paper I wrote with Michael, we showed that you can derive this equation from statistical mechanics. Now the idea is you can extend it also for this time-dependent case without too much extra work. You have actually an extra result that you can study the correlations of the system across time. So you can do optimal fingerprinting at multiple slices at the same time. You have to use a more generalized a correlation of the fields across times. And then you invert this gigantic matrix and gives you the result. Not obviously, it's always possible to do it, but there is a way to do it.
Not even invertibility.
Yeah, but you can do the weak invertibility, Moore-Penrose invertibility, and it will work. You do like an SVD decomposition and cut the. So there is a way out there.
Yeah, another question here, I think you'll be able to have second one. Yeah.
So if I understand correctly, Valerio, this response theory is a true linear theory, right?
At this stage, yes, but
And I think it's quite straightforward that whether you have stationary or some non-stationary states, you should be able, at least in principle, to figure out this bifurcation difference when the state itself loses stability over the years. For phase tipping or rate tipping, they are truly nonlinear responses in the sense that your reference is not so much your base state, but something else.
I know.
Which is next to it. So I was curious how you guys.
I know, yes. It's a no-look. That's one of the key challenges. So one possibility could be, but again, maybe it's not enough. Of course, you can, if you do linear response, you also can do nonlinear response. It's just, double the size of the calculation. And you can try to see whether that gives you further information. But still, it could be just too local to understand that. So let's put it this way. I would like to compare, even if I'm aware that the object that is critical for p-tipping or r-tipping is far from the attractor.
Too far. Why not, if you could do some linear theory on that object relative to your base object, the object is not stable, so it's you have a lot of divergence and you have to get rid of. And
yes, I'm trying to see whether at least as I would say an indication that loss of resilience, so not to dictate where p-tipping occurs, but to tell where it could occur. I think a possibility could be to see where in your period your basically response operator has a spike. So it could have a spike, which of course does not indicate necessarily, let's say, divergence, but it's a good, could be a good fingerprint of the divergence. I honestly, I don't know, but that's something I want to try. But I'm aware, thanks for making this observation, yeah.
I think we have at least two more, one Freddy and one there. Yeah, so Freddy.
Yes, I have a general question.
Yeah.
Maybe it goes beyond control. So in a very complex multidimensional system like that, bifurcation often the ones increasing. Like small dimensional systems.
Sorry, I couldn't catch that.
Bifurcation are sometimes are of different type.
Oh, yeah, sure, yeah.
So for instance, you know this war for a long time when people show up bifurcation, the cascade of
Yes.
small scale bifurcation, so some of the old work, but they also say.
Yeah. Freddy, can you speak louder because I think here
Oh,
nobody
sorry.
understands you. Do we have a microphone? In fact, that's a good point.
So if there is a tipping point of this type, so it seems, I don't know the answer. Should you finish that in such a case where you are the cascade of events should linear response theory?
I think it will tell you, I mean,
Would it be useful only for the first?
so it will tell you that there is the first because it's a local theory. Now the devil is in the details, in the sense that then you have to do the analysis in the proper functional space to see basically what happens at the border of the attractor. But you should see the first loss of stability, not the full cascade. I don't think you can see the full cascade. So now, as an example, in the case we have studied of a boundary crisis, I do believe that you will see this loss of stability. Again, so the idea is, I believe that this the sort of criticality of the Koopman expansion will emerge also in a non-simple bifurcation case. That's what I think.
There was one last question still, I think, and we.
Just very general question. Do you think it's possibility that we do fingerprint for local jump process? I thought.
Yes, from jump process. Yes, because in principle, yes, everything goes down the same flow of equations. Yes.
And then what would be the state, the physical integration of the state? I mean, for Markov jump process.
Of course, you have to think it not on the individual event, but in an ensemble sense, right? So anyway, if you do, that's something that one of our PhD students is now trying to do with Larissa as well, Ben, is to take, let's say, a simple bistable system and do a Koopman analysis with Levy noise and do the Koopman analysis. I don't think this has been really done so much. So that's something we want to learn. Of course, what is the subdominant mode? How does it look like? What happens if I change the topology of the potential? I honestly don't know the answer, but something must be there.
Okay.
I just want to, sorry.
Yeah.
Say too much. Freddy made this comment and you answered them. So that was clarification. I think it's interesting to comment on this because when you look at the Koopman operator, you get some indication of some stationary measure or something like that in the end. And there's two types of bifurcation you can have. You can either the stationary measure disappears and jumps to something else, or just the nature of the stationary measure changes. And that's what you cannot see in this operator theory. So you should have stable spectrum and the dynamics changing drastically. You see nothing because the state of the eigenmode is correct. And this is the problem of the operator. The eigenmode changes.
Yes.
You don't see it in the spectrum.
Okay, the eigenmodes will
This is the problem of the.
No, in this case, it will not work. So now no. In this case, if I have if I have a case where there is no signature of the tipping point in the spectrum, then the argument fails. Yeah, but I mean, in many cases where we have critical, I think that if you have a critical slowing down, then you will see it. If you have it, then you will see in this method. In that case, you will not have a critical slowing down. Well, the loss of correlations, I mean, if you, no, because otherwise you will see it in the Koopman spectrum. I agree that not all tipping points will be associated with critical slowing down. I agree with that. But if there is a critical slowing down, I think this is a way to see it. Yeah, I mean, not.
We started a bit later, so if there's
Just a
very
quick,
quick last
just a quick question. So after this time-dependent Markov
Yes.
operators, you talked about a system, I think, with Levy noise.
Yes. Oh,
And-
before. Yeah.
Oh, before. And is it something like white noise, and then sometimes you have jumps that you?
No, usually you tend. I mean, the expert is Jin Chao, but you tend to regularize. So you add the Levy process, but you keep a bit of Gaussian process to regularize the system.
Yes.
Yes.
Was it a time-dependent problem? So did you?
No, this is not. That is
okay.
no, that is not. So that's no. That's
So
separate.
It's a near throughout.
Yes. Yeah.
Thank you.
Okay, I think we're good. So
Yes.
thank you, Valerio.
Thank you.
Very nice.